So, we will continue from where we left yesterday. We were looking at the analysis of PM. We will look at different methods of measurement quantification for the entire range. So, one of the we were looking at gravimetric measurements which involved a collection on a filter media versus other techniques which are things like optical. So, optical techniques include both the measurement of the optical diameter or by the aerodynamic method. So, optical methods both the APS, which is aerodynamic particle sizer, which is also an optical method because it uses lasers to track the particles. The other method also uses a laser to measure scattering, to scatter off the particle and measure the angle of scattering and all that. Both are optical methods, but they give you different information. One gives you optical diameter, other one aerodynamic diameter. And then we also looked at something called as electrical mobility, which is the DMA. The electrical mobility diameter is a different size, it is a different basis. So, all these three are not the same. So, if you want to compare these three data sets, you have to do an experiment with the same kind of particle and then see if these diameters are the same. There should be correlation between these three. So, one has to be careful about this. Generally, they are nearby, but they are not exactly comparable. So, something which you say is 10 microns aerodynamic diameter may not be 10 microns in an optical diameter, and their behavior may be different. So, if you are looking at PM10 from a respiratory point of view, the PM10 that you get from a optical diameter may not match exactly with your PM10. There will be some variation, and you have to find out what that correlation is based on very carefully planned experiments. So, again, as with any other analytical method that we are looking at, we need standards. We are looking at optical diameter versus particle aerodynamic, we need standards. The standards here are standard particles. Standard particles means the standard which means there are particles that are known to be of a specific size and a specific. So, standard particles typically, I would like to have standard particles as spherical of a certain physical diameter. We know specific physical diameter and density. If I know this, so the definition of aerodynamic diameter is the mobility of an equivalent particle, spherical particle of a certain diameter and density 1 gram per. So, you choose a material which for the density is close to 1 gram, and that is the standard. So, based on that we define the other whatever these things. So, we define the optical diameter. What is the difference between optical diameter and the electrical mobility diameter, optical diameter, and the APS, the aerodynamic diameter, how close it is in terms of that. So, the instrument is you calibrate the instrument using standard particles like this, and then compare it with the same thing you do it with other instruments and say what is it that giving. So, whatever this says as 10, what is that other instrument saying. So, you make a correlation like this. The simplest way is to get these three instruments and run it at the same location if you do not have a standard, and then compare the particle size distribution or the numbers that you are getting in what is supposed to be PM10 and one instrument is giving, other instrument is giving PM10. How does it vary? Is this maybe a difference? There will be a difference, and this is usual, that is normal. So, you have to use this data carefully. You can't just blindly use one classification for the other. Okay. So, we are also talking about the advantages of using a filter, the purpose of using a filter. One is composition. One of the main things is composition. Second is mass. See, mass is a very fundamental quantity. people want to see particles. If I show them a filter paper that the sample that you have collected is dirty, this is the mass that is there in the atmosphere, people will believe you. What I mean by people is, you have to make decisions based on your ambient air monitoring, based on, you are going to make policy decisions, which means that you have to explain to some regulator somewhere that this is happening and therefore this means some process may have to be controlled. Everything costs money. So this is this big link that we talked about in the beginning of this course to economics and social policy and all that. So you need to show, if I show them optical scattering and diameter, then nobody will believe it's a black box. It says I don't know what you are punching. You are doing some programming and you are showing some numbers. I don't believe anything that you are saying. So physical mass shows that it is there. Okay, even though it doesn't give you full information, it gives you a very staggered information. It gives you time average information, but it's still there. It's physical evidence that something is there. Yeah. So that's one of the main advantages why a mass-based detector is still used. But as we go deeper into the problem, this mass-based detectors have limitations, severe limitations, and we would like to go ahead and understand more about the physical processes happening in the environment. We would like to have more real-time and distribution-based instruments. So you can imagine if I use an SMPS, which is the DMA and the particle CPC that we discussed, how much of information can you get from a single, if you sample for one day at a roadside, you can get a lot of information. You can get tons of information, you can do data analysis on that, all kinds of inferences can be made. Okay. So composition of filter media is a very important thing. So you would like to see what these particles are. So one of the ways in which we do that is by looking at composition. One, shape and morphology. Okay, shape and morphology. You can look at shape and morphology by using microscopy. So this is these are images from a scanning electron microscope of particulate matter. So the first image here, this one, is a blank. This is the image of a filter. The filter media looks like this. It has, you can see a scale here. I am not sure you can see it very well, the scale going from here to here. I can't see, I think it is about 10 micron, yeah, something around that, yeah, it is about 10 micron. So you can see that the filter size itself is quite small, it's an order of microns, and then particles are all kinds of shapes and sizes. You can see this is from a cascade impactor. This is from an impactor in which this is 10 to 2.5 microns, this is 2.5 to 1 microns, 1 to 0.5, 0.5 to 0.25 and less than 0.25. So you can see that particle size is generally decreasing as you are going down the order. You can see here the particles are very small and they are stuck on the filter. There is not much difference between this image and this image, the first image and the last image, the blank and this one. But you can see particles are still there, they are stuck on the fiber. And this is one of the important things that you need to remember, that particles, even though the opening of the filters is much larger than the particle size, the particles can still get trapped on a filter by inertial impaction and interception. So filtration works like that, it does not work by straining. What we call as straining is where particle size is smaller than the particle, that is straining. That is like your tea strainer or one of these. This does not work like that. If you were to do straining, no filtration at this level will work. So they rely on, if you look at a filter, this is a few microns thick fiber, the filter is about say 100 microns thick. So you have about 10 layers of filters. So this particle has to go just to change direction, and in the process it will hit and it will stick onto the fiber, and the small particle will stick on the fiber. So you can see that. You can see at the edge of all of these fibers, you can see this is the same phenomenon that you see in your house. If you have a mesh, a mosquito mesh or something, you will have dust that is collected on the mesh. This is very small, much smaller than the opening that is there, and this is the same principle. There is wind blowing across, it will get trapped along on the sides and so on. So you have physical particles. You can also based on the electron microscope also has a tool that is called as the energy dispersion spectra. This is called as the EDS or the so I can go and go deeper into the this thing, and I can focus on one particle, and I can. So electron microscopy very briefly works in this manner. You hit a in general microscopy, the resolution of particles depends on the wavelength, and wavelength depends on energy, E equals hc by lambda. But visible optical visible light has a wavelength limitation, so therefore the resolution also is dependent, reduced, not goes beyond a point. So if you want to have higher resolution, you need higher energy, and electrons, the energy that electrons have are much higher, and therefore it corresponds to a resolution, wavelength resolution which is much higher. So the way it works is this: electrons hit the particle, and some part of the because of the density of the particle, some electrons are bounced back, they are scattered. They are scattered and they are collected by a detector that is sitting at some angle, and as electrons are hitting each portion of this, it is scattered, and the scatter creates an image. So the energy of the electrons that is going out creates an image of that particular spot, and so the image, if it cannot go very deep, if it can go very deep, it will be a weak scatter. If it cannot go very deep, which means it is bounced back immediately, it will be a bright scatter. So based on that, you can get the basis of the shape of the particle, okay. And corresponding to this energy that is coming out, there is a wavelength, there is an corresponding to the radiation that is coming out, scattering, there is a wavelength energy and a wavelength, okay. And so, and we talked about it a few classes ago in emission, I think atomic emission spectroscopy, and one more, some other topic, I do not recall right now. So this gives a characteristic this thing, signal. This is called as energy. So this relates to the structure of the element, and there is an energy that is coming out, and based on that you can find out what this particle is. This is very critical information, because this is like a signature of the particle. So you have a particle, if you collect particulate matter, say in a roadside environment, and you go and do this kind of analysis, and you do elemental analysis, you can get very nice information about it. If you go to a very specific environment, say indoor air, and you are seeing say only carbon, there is nothing else there, so you can know that there is some carbon source in this particular location, and so on. So you can get fair amount of information, but the downside to this is this particle is about 10 microns or 5 microns, right. How do I know there are millions of particles in this small sample I have? I am not sure if all of this is the same. So you can get some idea about this, but you can't use this anywhere. It is very difficult to use this. For this you need little more macroscopic data and average data. For a large number of particles you need to have elemental compositions. So people do not use a lot of this in the analysis. So that PM, so if you want to do the composition of PM, you have two options again. You can do, so this, you can look at organic or inorganic, okay. So if you are looking at organic, you know the instruments that are used for organic. We saw that already in terms of the water. If you want to look at organic chemicals, there are a set of instrumentation that you can use, starting from the GC or LC or any of those instrumentations we want to use. So which we already know the instrumentation. And we know that this is PM in air, this is your source, particles are coming from here. So it needs to PM, from the PM in air you need to pull out, extract the, you have to extract this component A into a suitable solvent, and then we can process the solvent for the sample, for the instrument. So, depending on GC takes a solvent like hexane or dichloromethane or something, you have to pull the PM, you have to pull the constituents. Where are the constituents? The PM, so let us say the particle is there. This particle itself may be an organic particle, which means that you have to dissolve the entire particle into a solvent. So, that is one option. Second option is if the particle, if the organic material is adsorbed on another particle, then you have to pull these particles out, we have to desorb, you have to dissolve or desorb. Desorption also can be considered as dissolution, either way. So, this if A is stuck here or the entire thing is A, either way is possible. Okay. So, what may happen sometimes is you may have a particle of sand, silt or clay on which some organic matter may be adsorbed or sticking, organic carbon, humic material, or you may have a standalone particle which is only carbon. Yeah, that happens in case of combustion sources. The only small particle that is there in the atmosphere is entirely carbon, organic. Okay, it is made of either the unburned fuel or any byproducts or carbon, soot, elemental carbon. These are all possible. So, any of these things is possible. So, when you are looking at these, the GC instrumentation like GC, it is very unlikely. So, GC will look at compounds which have some structure and some this, we saw how it measures it, FID and all that. So, typically it is mostly this category for carbons, compounds which are organic compounds which are adsorbed on something, or they have a composition, and not just carbon, not just elemental carbon. Elemental carbon will not dissolve in many of these things, it will stay as elemental carbon. So, here again there is a distinction. So, if you want to pull out look at composition of some of these things, if they are adsorbed on something else, they will nicely show up in something like the GC or the LC. But if it is pure carbon, it may not show up in this, because it will not dissolve in anything, it will sit there and it is elemental, it is a solid particle by itself, pure carbon. So, for that you need to have a different approach of measuring it. So, there are tools for doing it that are different. Okay. So, I will just classify it, I am not going to discuss in detail. So, when we do organic analysis for PM, we do what is called as OCEC analysis, is called as organic carbon, elemental carbon. Okay. What we mean by organic carbon is the carbon that is part of CH, NO and so on. So, it's a compound, it's any compound that we have seen in the list of organic chemicals. Elemental carbon is just carbon, it is just carbon, nothing else. Soot, we can also call it, it's also called as black carbon, it's also called as soot. The various names for this elemental carbon. So, organic carbon and elemental carbon are generally associated with different sources in the environment. So, there is an instrument which will measure the organic carbon and elemental carbon pretty much on the same lines as what a GC works, but it is very dedicated to this. Okay. So, the organic carbon, elemental carbon instrument, we will get to that in a minute. The other kind of that is all, this is two of them. The other kind of analysis that you have is inorganic analysis. So, inorganic analysis you can do two kind of things, you can do elemental analysis or you can do ions. You can get what is present in on the particle by either of these methods. Okay. Both of these gives you different information, you can combine this information, so it gives you, a full picture of, you do both of them. So, elemental analysis will give you, for example, it will give you total sodium, potassium, lead, calcium, iron, chromium. So, you are doing all these methods that we have discussed last week. So, in that bunch of this, mercury and everything. So, there are different methods for this, there are different, this is total. Ion analysis specifically looks at ions. Ions means there is Na plus, K plus, so on, Cr3 plus, Cr6 plus, Cl minus, NO3 minus, SO4 2 minus. There are cations, anions separately. Okay. Elemental analysis you can do using an ICP MS, ICP OES as we discussed last week, or the atomic absorption spectroscopy, the AAS3 instruments available. This we use a technique called as ion chromatography. So, there is a difference between these two approaches. Okay. ICP, AES, OES, all of this have, everything is done in terms of, this is total, everything is completely, ion chromatography is just the ions. Okay. Now, one limitation of the elemental analysis is that it related to how you do the elemental analysis. So, like in the previous figure, you have the instruments, and you have the PM in air. To take it from here to here, you need to extract it into something, you can't directly put it. What will you extract with in the case of organic material, if you want to extract organic compound from particulate matter, just like what we do for water or soil, solids, we extract it using an organic solvent. So, the procedure there, here, this is for the organic, the procedure here is you take the filter paper and you extract everything. That only way you saw the SEM image, the filter paper and the particulate matter you can't separate it very well, it's several layers deep. It's very difficult for me to pull out all the particulate matter. So, I am better off if I am doing mass balance. If I say in a filter paper I have X micrograms of particles, I would like to do a mass balance on that. I would like to know how much of this X micrograms corresponds to carbon or some element. So, I need to capture everything, I do not want to disturb it. So, I take the filter paper and extract it as it is. Okay. If I am extracting with an organic solvent, what is the possible interference that can happen in your analysis extraction? You are extracting with an organic solvent, the filter material itself may dissolve, or depending on what the filter is made of, it may leach out. So, what do you prefer, like what we did for sampling, what do you prefer is the filter paper material for organic analysis? You go back to your discussion on liquid water, analysis of elements in water. What did we discuss there in terms of, for organic analysis, the water sample is preferably collected in glass. So, the preferable filter matrix is also glass. So, we use a glass fiber filter. There are glass fiber filters, but glass fiber filters also contains a binder sometimes. Even though it is fully glass, sometimes if you just have glass fibers, it is very brittle, it will break very easily. So, there is another one called as quartz fiber filter. You can have glass, regular glass, low grade glass, you can weave it into fibers and you can do that. You can also have quartz fiber, which is very high grade glass. The difference in quartz can withstand very high temperatures, it can go up to 1000 degrees, it will not disintegrate, it will stay as it is. Okay. So, quartz is very high temperature this thing. Glass fiber filter may have a binder in it which can leach out when you do this. Okay. So, the preferred filter matrix is quartz for organic. So, nothing will happen if you put any organic solvent, there is only glass there and there is no other binder. So, it will, yeah. but glass, because of this, quartz fiber filter is very brittle. Quartz fiber filter is not very preferred for mass measurement, because you are taking the filter and putting it into a filter, by the time some corner edge of the filter may tear and go away. So, you will get an incorrect mass measurement. So, we do not use quartz fiber for that. On the other hand, if you are doing metal analysis, what is the filter, what is the extraction medium that we generally use? We have not discussed it. What do we extract metals with? Generally all elements from high school chemistry. What is the material used for extraction of metal elements? What solvent, what liquid can we use? Huh? An acid. Which is the acid that has that dissolves everything, or HNO3. So, all nitrates are supposed to be soluble. So, the generic solvent is HNO3, but sometimes you also add other acids along with it. Sometimes you, depending on what the matrix is. So, in general, you can go and see the actual method for specific elements. You have specific combinations of acids, but HNO3 is by and large the basis. Okay, so you used so for extraction of metals from soil, sediment and soil, which is a very dense matrix, yeah, lot of material, we use concentrated HNO3. But the filter paper has only a few micrograms of this thing. You do not need to use concentrated HNO3. The amount of metals here is very small, and it is a very mild process. So, we generally do not use concentrated HNO3. You can use dilute HNO3, 10%, 20%. The specification is given. So, it is extracted and separated so that the acid extract is taken away. So, when you use HNO3, there is one element that will not dissolve in HNO3. Do you know which one? Huh? There is one element which will not dissolve in HNO3. And you require hydrofluoric acid for that, which is a very dangerous substance. So, you do not use hydrofluoric acid often. When you use hydrofluoric acid, you have to have a separate lab, separate conditions for all that. So, which element can only be removed by hydrofluoric acid, dissolved in hydrofluoric acid? Any guess, anybody? It is a major constituent of particulate matter in the atmosphere. Lead? No. It is used in the semiconductor industry a lot. Hydrofluoric acid is used in the semiconductor industry for this reason. Silicon. Silicon is a big portion of crustal material, right? Resuspended road dust, soil, silt, clay, all of them have silicon. You cannot measure silicon by extract silicon by this method. So, in all these methods you will see, and footnote there, that you can't use silicon. You can't measure, you can measure silicon in the ICP, but the extraction will not contain silicon. So, you will see silicon in the data, but extraction will not hydrochloric. So, you also have to understand that if you use hydrofluoric acid to extract, you can't put it into the ICP. It will destroy the ICP. The ICP has glass components and all that, it will create a problem there. So, we do not, silicon is generally not analyzed in these methods, but you need a non-invasive method, a different kind of method, and you have already seen that. One of the methods that is used for silicon is what is called as X-ray fluorescence, which is on the same principle as the EDS, energy dispersive spectra. You hit X-rays and silicon will give a characteristic wavelength as the emission. You measure that. So, the filter paper itself, you have all elements, you can use X-ray fluorescence to get all elements instead of doing ICP. It has problems because there are, all spectroscopy have problems in terms of, the extraction method is very simple because there is no problem about what is the depth of the sample, everything. It will take away everything, it will remove everything. It is a brute force method. It does not have any, you do not have to be very precise with it and all that. Okay. So, the point we are making is, if you want to do extraction with nitric acid, what is the filter bit paper that you need to use? You can't use glass because glass is elemental. Glass is a bunch of, say, You can use quartz, but quartz is again, it's still metal, and quartz is very expensive, we do not want to use quartz. Cheaper material for filter, what can you use for elemental analysis? Metals. Same way, what we use for water, metals in water, we use plastic bottles. You can use a plastic filter. So you can use the filter paper that we use can be nylon, you get all kinds of polymer fibers. You have nylon, Teflon, polypropylene, polyethylene, polycarbonate, all kinds of things. Okay. Teflon is preferred because Teflon is considered to be inert. There is no binder, nothing. It's just Teflon. It's nothing, and it's the Teflon filter paper is used for analysis of metals, at least in the X-ray fluorescence and in ICP methods. Yeah. Teflon is expensive, so you can use nylon if you want for some cases, but preferred Teflon. You can also use Teflon for mass measurement, because glass fiber is a very delicate fiber, it may tear and all that. So, Teflon can be used for actual PM measurement. You can collect the sample, take it and put it in a balance and take it out. That is actual full mass measurement. When we say mass measurement, it is combined mass, it is PM mass. This what we are talking about is the composition analysis. So, in a given site, say outside this building, I want to get the full composition of everything. How many filters, minimum number of filters I need to use? I can't use the same filter for all analysis, which means I have to use multiple filters at the same time. Yeah. So, it is a bit of an inconvenience. So, you have to use, if you have multiple concurrently, multiple filters concurrently. You can at least have quartz fiber for all the organic analysis. You have Teflon for metals. You can have one more Teflon or nylon for the ions. The ions, what is the extraction solvent for ions? For metals, it is acid, organic it is carbon, organic solvents. For ions, what is the solvent for ions? Water. Ions, water. Water is enough. But is there a specific nature of the water that we want to use? Can we use tap water? Yeah. We have used deionized water because the extraction ion analysis using water, we use what is called as deionized water. We use water that is as deionized as possible. So, it is not possible to get 0 absolutely, but very, very low amounts of deionization. There is a process called as ion exchange, which removes all ions and puts to the extent possible, it makes it neutral and sends it in this case. So, again the same rules of blank, minimum detection limit all apply depending on how. So, this is a problem with metal analysis, because metal analysis you are using solvents and your sample is exposed to air. There is always a chance that something from air will fall into the sample, which means your false positives are likely to be higher. So, your minimum detection limit is likely to be higher, which means sensitivity is lower. Now, you can't go to as low concentrations as possible, because for example, if you have deionized water, you cannot get deionization beyond a certain level. So, therefore, you cannot detect ions concentrations below a certain level. You always have to take that minimum detection limit, and that is what it is. So, there is nothing you can do about it unless you get. So, there is a lot of problems. So, when you open a bottle of water, there is a lot of particles in the air, they will all get in the time you are processing, extracting and all that. So, you have to run a method blank only with the deionized water just to see what are the ions that are coming, and if that is affecting your analysis. So, method blanks becomes very important in metal analysis if we are doing aerosol, because the amount we are talking about in aerosols are very small. Okay. If you are talking about very large quantities, little bit of error may not even show up, but we are talking about very small quantities, we are doing trace analysis, this becomes very critical. So, ion extraction is done using deionized water. So, you have at least 3 filters, one for each, and they are running concurrently, which means that you need to have 3 PM samplers or 3 of these samplers running concurrently. So, to do this there is what is called as the speciation sampler. Commercially it is available. So, it is a multi-channel sampler. So, you have multiple channels, they are all doing the same thing. It is attached to one pump and the pump distributes flow in these 5 channels. Flow rate is adjusted so that they are all the same flow, so that the cutoff is the same. So, if you are measuring PM 2.5, all of them are measuring PM 2.5 at the same site, the intake is the same location. So, I can get data on the quartz, organic, I can get organic which includes OC, EC and everything and other things, and on the metals, elements and the ions, everything happens in the same site. So, I can get a good picture of course, there are statistical problems in this, because even though there are even though they are the same site, there are 3 different filters, they all may not correspond to the same value. There is always a chance that they are slightly off. So, we have to do a lot of statistical replicates and find out average and standard deviations and all that. So, that is very important in this. So, this is used in what we generally call as source apportionment. We will talk about this later if we have time towards the end of the course. What essentially this source apportionment does is it tries to ascribe what is the contribution of different sources to pollutants in the atmosphere. So, the source apportionment term is a general term, it applies to anything, it applies to water, soil, air, everything, but in the air now it is applied mostly to air, because the air is very complex medium and materials from different sources can come far away from the source and mix, and therefore it is important for us to find some way of doing it. So, the information required for source apportionment comes from this kind of speciation analysis. For this we need the speciation sampler, otherwise we have to have 3 samplers next to each other sampling 3 different species. Point we are trying to make is filter paper choice depends on what you want to analyze. You can't do one for all, you can do one for all, it will be full of errors, so you have to have a lot of control samples. For example, if I were to do extraction of metals using, I were to use only glass fiber filter for everything, I will have a lot of leaching, extraction of other things. My blank filter paper signal will be maybe so huge that any trace I am getting there will be lost in it possibly. Okay, so, I have to do a lot of cleanup and a lot of my MDLs will all be low and high, so on. So, sensitivity of the method will go down and so on. So, because information like this is used in policy making, they are very careful about this. But if you want general information, you just want to know what is there, you can probably do it with one filter and then get an idea. This is approximately, these are the things which are there, and therefore I will then refine my study again. Okay.